All right.
Hi.
Okay. Hi. All right. Okay. So last time we talked about Charles Darwin and his basically declaring all of the evidence in favor of biological evolution, and I want to take a moment to ask this question and have us talk about it together. So why did almost all of the scientists at Darwin's time believe in fixity of species? So you have this concept that's called fixity of species. Whoa, of species. And the idea here is, bless you.
Thank you.
Species persist unchanged through time. So the first part of chapter 22 that we've talked about so far was Darwin's journey around the world on the HMS Beagle, his work as a naturalist on the ship. We talked a little bit about Alfred Russel Wallace's work as a naturalist upon another ship, this idea of natural selection being the driving force of biological evolution, and overwhelming evidence in favor of biological evolution. That species don't persist unchanged through time, rather they change through time and through space, right? And Darwin asked questions like, why would God create all of these different species of finches on these different islands? It just doesn't make sense. What makes way more sense is that they spread there from the mainland and then changed through time. Yeah?
Is the last word of that definition time?
Yes. Oh man. Unchanged through time. It is Wednesday and I'm having some...
October 3rd, Wednesday.
It is...
Mean Girls. What did you say?
I don't know. Sorry. I have seen that movie, but I don't remember. Anyways, I'm not thinking really clearly because I'm having allergies. Hey, guys, let's focus.
Mean Girls is not.
You said.
Were a lot of those scientists Christians?
They were. A lot of these scientists were Christians at the time when Darwin published this. When Darwin published On the Origin of Species, as well as Alfred Russel Wallace's essay that natural selection was the driving force of biological evolution. And so, is that why? Do you think that that's why almost all of the scientists at the time embraced fixity of species? Is it because they were Christians? Tori says no.
Wait, what's...
Any other ideas? So really, if it's because they were Christians they embraced this idea, which suggests that the Bible teaches fixity of species. Katie.
Well, it's in theology. It's like God stopped creating after the.
Okay.
So then they probably didn't want to assume that if something was happening with the creatures, then it would be God who was creating more.
Didn't want to allow for too much happening outside of God's active involvement. Yeah, Mark.
Just really fast. When did Darwin start doing this?
Well, he published On the Origin of Species in 1859, along with Alfred Russel Wallace's essay. But Darwin came up with his idea of natural selection driving biological evolution in the 1830s.
Because I know that I don't know if it persisted to this time, but a lot of the medieval and
yes.
world and even some after that was mostly Christian in Europe.
Yes, absolutely.
So I'm thinking it could have still persisted.
Yes.
To this time. So basically, saying most of them are Christians at this moment,
or at least heavily influenced by the ideas of the church. They may not have been Christians. In fact, many of them were probably deists that God had created and then just basically stepped back and let everything just run. But they were heavily influenced by Christian ideals. The main reason everybody adopted the fixity of species is this was Aristotle's idea. Have you seen this name before?
No, never.
Never, ever, right? Aristotle, probably the most widely read of all of the Greek philosophers.
Even Plato.
There was a rediscovery of Aristotle's work during the Middle Ages, and Aristotle's ideas heavily influenced every aspect of European science. And Aristotle was a big proponent of fixity of species. That these species are not perfect, but they are static, that they don't change through time. Okay, that they basically remain the same unchanged. And because virtually everybody embraced Aristotle's idea of the fixity of species, virtually everybody denounced biological evolution. And so Darwin, the reason why he sat on his ideas for 2 decades is because he knew that in order to really convince everybody, his arguments had to be sound, because he had seen several people in the past propose biological evolution and just been completely destroyed by the scientific community. Completely destroyed. So he sat on it for 2 decades until he got an essay from Alfred Russel Wallace that basically proposed the same thing Darwin did, but in a much simpler explanation, without the robust arguments that Darwin had put together and then published on the Origin of Species. All right. So now, assuming biological evolution is true, which Darwin made a very compelling case, and we can see overwhelming evidence that animals do not remain static through time. Okay? So assuming biological evolution is true, what would you predict about the natural world? When you study organisms, what would you predict? Yeah, Isa.
That form is not its original form.
Yeah, so that's one prediction, that if you can trace that organism back through time, you should see evidence that it has changed through time. Good. What else? Kyle?
It's still going to change?
Yeah, so that if you study it for a long period of time, you should see it changing. And we've seen this with the Galapagos finches, which you mentioned last time, Kyle, and we've talked about before, right, with character displacement. 2 closely related finches on the same island, they partition the niche and you get character displacement, right? They become more different through time than they were at the point of introduction, right? And so we can see this happening. And the 2 areas where we find the most overwhelming evidence in favor of animals changing through time is in these 2 areas. Introduced species and antibiotic resistance. These are 2 of the absolute resistance, ANCE or ENCE? A. That makes sense because in... Yeah, no worries. It makes sense because in French it's resistance, right?
Hi, Erin.
Spelled the same? Yeah. Okay, so these are by far the areas where we find the most extreme amounts of change through time. So introduced species, what's going on here? Somebody tell me what this means. Mark.
That would be like I noticed like basically people on maybe like boats or maybe like by natural causes basically just like in basic terms creatures from like another region have been carried over either by natural means or human
Right, purposely or naturally. So by naturally you mean not by humans.
Yeah, basically like if a huge storm carries a bunch of bugs and birds.
Yeah.
During the night.
So when organisms show up in a place they've not been before.
Yeah.
Okay? And so what happens is when we have these introduced species, the native species often change in response. Okay? They've either got a new competitor, or they have a new food source, or they have a new predator. And so introducing a species provides enormous pressure on native species to adapt. Adapt or die, right? or actually it's adapt, die, or move. Right? Those are your options. Okay, and so the textbook talks about an example of invasive or introduced species of plants and native insects changing morphologically in response to that. The native species require the insects to get through a lot of flesh in order to get to where they can feed inside of the fruit. This introduced species, they don't need as long of a proboscis, and so the insect species that feeds on these introduced plants have much shorter beaks than the insects that feed on native plants. Okay? And so because you either have a new food source, or you have a new competitor, or you have a new predator, or you have a new parasite, okay, there's enormous pressure to change. And we can see this, and in very short amounts of time. By short amounts of time, I mean on the order of years, decades at the most, right, where we can actually trace it through time. What about this one? Antibiotic resistance. Yeah, Lydia.
So as like science has progressed, we've like come up with new ways to like treat different kinds of diseases, and those have been like adapting in response to that.
Yes.
So as we have to create new things to kind of switch those out, but they're becoming increasingly more resistant.
Yes. And so the best example of this, or maybe the most widely known example of this, is MRSA. MRSA, have you heard MRSA? You've never heard of MRSA? Okay. Well, even if you've heard of it, you may not have ever seen it written down. This is an acronym that stands for methicillin resistant staph. Let me make sure I spell this right. Okay. Staphylococcus aureus. Methicillin resistant Staphylococcus aureus. People rarely use the whole genus name for this bacterium and just call it Staph aureus or just staph. Staph infection? Yes, sir. You got it.
It sounds more important the way it is.
And so again, here, this introduced species applied enormous selective pressure on the native species. Our use of antibiotics applies enormous selective pressure on these bacteria, because the antibiotics are killing any bacteria that are not resistant. So any bacteria that are not resistant to that antibiotic are being killed. And so only the individuals that for some reason have resistance to that bacterium, they're the only ones surviving to reproduce. Meaning that in a very short amount of time, your entire population is made up by a number of now resistant individuals. Okay? And what you find when you read about this is there are three major contributors to the rise of antibiotic resistance. Three main contributors. One is overuse of antibiotics. Using antibiotics when you don't need them, maybe to treat viral infections where they're not going to do anything anyways. These are made to combat bacterial infections. Or in the agricultural industry, where you give your cattle antibiotics to just prevent any bacterial infections. Use it what you call prophylactically. Okay, they're not actually sick, but you give them antibiotics so that they don't get sick. Isa.
What are these three reasons, or these three things?
These are three things that contribute to the appearance or a number of antibiotic resistant forms. Yeah, so one is overuse of antibiotics. And again, that would be in agricultural applications, or when you use antibiotics prophylactically, you're not actually sick, but you use them to prevent yourself from getting sick. The other one is making new antibiotics. So again, first big issue is overuse of antibiotics. Second big issue is the continual development of new antibiotics. And then the third one is improper use of antibiotics. Not an overuse, but an improper use of antibiotics. How many of you have ever been prescribed antibiotics? How many of you have taken them until they disappeared?
Yeah, but not always.
See, this is what we call an improper use of antibiotics. So you have many bacterial individuals that have what you call partial resistance to the antibiotic. And the reason why they have partial resistance to it is they maybe have one of two genes that are different in order to be fully resistant to that bacteria or to that antibiotic. And so if you don't use your antibiotics until they run out, the chances of you killing all of those bacterial individuals in your body is significantly reduced. And then so what you have the potential for is that you've allowed some of those individuals with partial resistance to survive, where if you took your antibiotics until they ran out, it'd be much more likely that they would die. And now they can mate with other individuals that have partial resistance, and maybe their partial resistance has the other gene difference necessary in order to be fully resistant. This is what we call improper use of antibiotics. Yeah, Emma.
What's the average length that bacteria can survive?
A single bacterial individual, how long can it survive? I have no idea. E. coli replicates every 20 minutes when it's in like its rapid growth phase, and a number of bacterial forms are similar to that. An individual cell, I don't know the average longevity. It's a good question, Trinity.
So you don't want bacteria to be antibiotic resistant? 'Cause I know there's
No, you certainly don't. Because so this particular strain or this particular type of Staph aureus, MRSA, you can't treat it with what is the best antibiotic to use against staph infections, which means you have to treat it with some other antibiotic. And so, like say vancomycin, but now we've generated vancomycin resistant Staph aureus, and then so you treat it with a different antibiotic. And so what it does is it just drives the need for more and more antibiotics, which then go and drive the pressure for bacteria to become resistant to those forms. Yeah, Isa.
It's like people use too much of that bug spray stuff, they're repellent.
Yeah, and you get insects that are resistant to the insecticide. Is that what you're talking about?
Yeah, or like
Yep.
I used to live in Texas and like the mosquitoes are horrible.
Yeah,
Like,
they're
bug
resistant. Are they resistant to
spray, the bug
DEET?
spray.
Yeah.
What's it called? Off.
Off? Yeah, it's got DEET in it, which I don't remember what DEET stands for. Yeah, Tori.
Is that kind of like, I know my uncle, like, I think he was working outside all day one day and he sprayed bug spray like all over his like skin and stuff, and he forgot to like take a shower before he went to sleep, and he like was so sick of like everyone, and I don't remember what happened. But
It just
like,
absorbed that pesticide.
Yeah, and he like was like hallucinating.
Yeah.
It was really weird.
Yeah, it's not good. Skin is very absorbent, right? It's one of the reasons that allows you to like put icy hot or something on your skin and for it to soothe your muscle aches. It's because skin is very absorbent. And so if you spray yourself with insecticide or even you leave sunblock on your skin, you're going to absorb whatever's in it, and sometimes it can have really detrimental impacts. All right, so again, introduced species, antibiotic resistance. The theme here is when you apply enormous selective pressure, you get to watch animals change. You get to watch them change through time, illustrating this idea of biological evolution, that species are not static, that they do in fact change through time. There's a figure in your text that shows 4 key adaptations for antibiotic resistance. One is the actual resistance to the antibiotic. One is the ability to infect host. One is the ability to grow very rapidly, which leads to increased disease severity. And then one is allows them to exchange genetic material more freely with other bacteria, so that they can make other bacteria antibiotic resistant. And that's another big issue, right, with improper use of antibiotics, is now you allow other bacterial forms to survive to become resistant from the resistant forms. All right? Any questions? Thoughts? Concerns? Okay, what I want you to do now is I want you to take about a minute working with those around you, and I want you to come up with a list of things that you would expect to find, not as you watched a single species or as you studied a single species back through history, right? Looking through the fossil record or historical records on that species. But I want you to think of if biological evolution is true and actually transcends groups of animals, so not only do species change through time, but species are connected together through common ancestry, okay? If that is true, what would you expect to see as you studied living organisms, okay? So for instance, let me make this very specific, okay? If all mammals were to root back to a single mammal ancestor, okay? That at a certain point in time, there was a single type of mammal that then gave rise to all of the mammals we have now, okay? If that is true, what would you expect to find as you studied mammals from different groups? Okay, what would you expect to find? Take a minute or two, talk with those around you, come up with a list of features that you might expect to find, or just characteristics, all right? And you can make them specific characteristics, or you can be a little bit more general.
If all mammals came from the same one animal, then we find some similar features and traits, just like basically small features everyone.
Yeah, so if all mammals root back to a single ancestral mammal, what would you expect to see as you studied all sorts of different kinds of mammals? Yeah, what would you expect to see? What evidence would you expect to see in those mammals of all coming from the same ancestor?
Like they all have, like they're related.
Okay, yeah, and what would you expect then?
So we have some potential,
Yeah, absolutely. Yeah, so get specific. Get specific.
Like the other change where human was involved in more like adaptive.
Macro is basically very, very rich in
Yeah.
macro is like
What evidence you would expect to find?
macro
Like right now? Yeah. All right. So let me ask this way. What do you expect to find as you study siblings, knowing that they share two common ancestors, right? They share mom and dad, right? So when you meet Kyle's little brother,
He looks just like you.
what would you expect to find? You'd expect that for there to be some familial similarities. Their personalities could not be more different. Could not be. They do look very similar.
Like, is that Brandon or Kyle? Who knows?
Well, except for Brandon's 4 years younger? Almost 3. Okay, so you're closer than I thought. Yeah, but their personalities couldn't be more different. But you expect to see some shared features, right? Because they descend from the same ancestors. So which means if all mammals descend from a single mammal ancestor, what would we expect to find? Kyle? Similar structures. And what are some of those similar structures? Shh. Kyle's teaching us right now.
Body parts,
Okay, like what?
like the bones we have.
Okay, so even if our limbs are different, like I have an arm and a dolphin has a fin and a bat has a wing, you'd expect there to be some shared skeletal features, because if we all descend from the same ancestor, there's got to be modifications on the same original plan. Okay? Right? Does that make sense?
Yes.
Lydia?
We said similar genetics.
Similar genetics. So that mammals should be more similar to each other genetically than they are to non-mammals. Right? Because you would imagine they have a more recent ancestor shared than they would to other groups. Okay? What else? Yeah, Katie.
Well, don't humans have the thing called mitochondrial Eve? So it's
Okay.
something animals have mitochondria.
Mitochondrial Eve, the original ancestor for all the mitochondrial DNA. You know, a lot of this,
is Y chromosome.
and Y chromosome atom, a lot of this is in flux right now because with just huge amounts of data as people sending in their saliva to be analyzed for Ancestry with like 23andMe, Ancestry.com, and I did it too, and we're getting a lot more data. Shh. And so all of our ideas, not all of our ideas, but many of our ideas on human origins are in flux right now. It doesn't seem to be as simple, but yeah, I mean we can trace we should be able to trace human ancestry back to a small subset of individuals, right? Regardless of your particular view of how humans came to be human, right? Were they specially created by God? Or were they descendant from other biological forms? We should be able to trace ancestry back to a small group of original humans. Any other ideas of shared features? Yeah, Emma.
This is like totally off. Like, since they all came from one like species.
Well, assuming they did.
Yeah, okay, actually, end the situation.
Yeah.
If you bred like a bunch together for like a really long time, could you get back to the original species?
You could if they could actually reproduce together, which they can't unless they're really, really similar. So like a fox can reproduce with a dog,
They can?
sort of.
What do you mean?
Well, so you can sometimes make it work, but it won't happen on its own. You have to do like artificial insemination.
They can't have intercourse.
Right, but coyotes and domestic dogs will reproduce together and will form like a hybrid. Horses will reproduce with zebra.
Yeah,
and
I've seen that.
and so
That's called an okapi, right?
no, it's called a hebra or a zorse, depending on whether the father is a horse or a
It's totally
zebra.
different species.
That's called giraffe.
So, but what you find is when you take individuals that are on either side of are on either extreme and you breed them together, like different breeds of dog. Like so, if you took Chihuahua sperm and inseminated a Saint Bernard female, your offspring are going to look more like a wolf than they would the individual, or at least are getting more and more wolf-like. And after a few generations, you're going to have something that looks very wolf-like.
That's so cool.
Yeah. Anyways, so we have this term that is homology. And what it is a shared feature from a common ancestor. So a homology is a shared feature from a common ancestor. And so this, Kyle said, like some of our skeletal features. So there's a figure from your text where it shows a human arm, a cat's front limb, a whale's flipper, and a bat's wing. And there are similar skeletal components because they develop basically from the same architecture. And that's what you would expect to find if all mammals root back to a single mammal ancestor. The question is, would you also expect to find that if mammals, many different groups of mammals, were special creations? And we'll talk about that when we get into big macroevolutionary ideas. You find similar developmental features that all mammals share, and even all vertebrates share similar developmental features, but homology, a shared feature from common ancestry. You have another term that is this, analogy. Is that spelled right? Analogous?
No, it's A-N-A-L-O-G-Y.
Oh my goodness, what's happening here? Wow.
Are you trying to spell analogy? A-N-A-L-O-G-Y.
So far off that it came in autocorrect.
Is that better?
Yes.
Okay. Yes. Okay, analogy. Okay, or an analogous feature. And this is a feature with similar function but separate ancestry.
Ancestry?
Yep. So a feature with similar function but with separate ancestry. And so the kind of the textbook example of an analogy tends to be like wings in insects, wings in birds, wings in bats, wings in pterosaurs. Like pterodactyls. Pterosaurs is a general term for the entire group. Yeah. There's the Quetzalcoatlus. They're not flying dinosaurs. They're not dinosaurs.
Basically, they're just a
Contemporary with dinosaurs.
Basically,
but
they're a reptilian bird.
Except the idea is that birds are reptiles as well. So a reptilian bird would represent birds.
Birds
All
are
right.
reptilian?
Yes. All right.
What?
So an analogy, feature with similar function but separate ancestry. Again, wings in insects, wings in birds, wings in bats, wings in pterosaurs. Yeah, Michelle.
I have an English question. So, what is the difference between the ancestry and ancestor?
Ancestry is like your entire heritage, your heritage. An ancestor is a single individual. So the ancestry is the whole picture. It would be like the entire tree, your entire family tree, and then the ancestor would be a single leaf on that tree, a specific individual. That's a good question. All right. So do these two terms make sense, the differences? Okay. So we're going to take ourselves a lecture break. Let me pause our recording. So with homologies, there are two different types of homologies, okay? Two different types. So these are all homologies up here on the board, right? All different homologies. They come in two forms. You have forms that are called plesiomorphies. Plesiomorphy, okay? That's one form of homology. The other form is a synapomorphy. And yes, I realize that those are highly technical terms, and yes, I realize that they're awesome. Right? I realize both things. You're welcome for both. All right, so plesiomorphy, this is a homology that is present in an ancestor outside the group. A synapomorphy is present only in the group. So going to our examples here. Sorry. We need to go through and I want to label these homologies as a plesiomorphy or a synapomorphy. Mark.
Does plesiomorphy have anything to do with the plesiosaurus?
No.
Similar.
No. I mean, pleiosauruses have plesiomorphies, and I'm sure the root means the same in both, but I don't know what that root means in Latin or Greek, wherever it comes from. All right. So plesiomorphy means it's present in that group, but it's also present in an ancestor that came before that group. Okay? Whereas a synapomorphy is found only in that group. So hollow bones. Is this found only in birds, or would it also be found in the ancestors of birds? This is only birds.
Wait, what?
How did that even come about?
It's an excellent question.
Oh, I get it.
How can you tell?
Because other
It's present only.
Because we don't have any fossils of other things that I know of with hollow bones besides birds. Feathers. They're feathered dinosaurs, right? They're feathered like raptors. Y'all seen? Oh yeah.
Then raptors.
Velociraptor.
Oh yeah, the velociraptors had feathers at least right here, possibly over their entire body.
Weren't velociraptors only like 2 feet tall?
Velociraptors stood about waist high. They were about 6 feet long, snout to tail, but they only stood about this tall at the most. Many of them were more like here. But what they use in the movie is a Utah raptor.
Utah.
Similar, but much bigger. You know, stood 6 feet tall or
Really
so.
cool.
So there are animals that exist like
You
that.
see, there are other raptors besides just the velociraptor.
Yes, oh yeah. What about talons? Yep. Beaks, laying eggs,
Ancestry.
building nests. We have a number of dinosaur species that also build nests. Reason to suggest. What about wings?
That's a big nest. Ancestors.
Yep. All right. So felines, retractable claws. This one is probably just this group. What about weaned children? Ancestors, right? That's something you find in all mammals. What about paw pads in canids? This is this is just for dogs. Live birth,
Or P.
P. Fish, scales.
Ancestors.
Well, fish are interesting. I mean, fish.
Wait.
Before you, I mean, fish. The idea with fish is these are like the original vertebrates. The thing before a fish, it would be so clearly not fish that
So it's
you
just-
wouldn't classify
it's
it as.
just fish?
Yeah, I would put this as S.
Well, yeah, because what's the ancestor of it?
Gills. Gills were probably present in ancestor. Fins, though, are also something that you find in just the fishes. Okay? And so when we do an activity like this and we go through and we determine, is this a plesiomorphy or is it a synapomorphy? And if it's a synapomorphy, it's found only in that group and it becomes a useful tool to use to build our phylogenies or our phylogenetic trees or our cladograms that we talked about last time. Right?
Yes.
Do you remember talking about those?
Yeah.
Okay, and so we can build a phylogeny that, say, looks something like this.
Thank you.
Looks like a playoff brush.
Okay? That looks something like this. And I'm not going to fill in animals because I want to keep this very general, but I'd like for you to draw this because I'd like for you to be able to reproduce something like this. Like, I don't know, let's say hypothetically, you were asked to describe a synapomorphy and how it is used to build phylogenies. Right? And you'd be like, you know what? Dr. Engel prepared me for this. I'm going to nail this on the AP exam. And not only am I going to nail it, but I'm going to give a unique take on it that the graders are really going to enjoy. And I'm going to do a phylogeny of parasites. Right? And so what we would do is all of these branches would be made and you would reference a specific synapomorphy. So here, synapomorphy 1, that is present in all of these groups. Okay, synapomorphy 1, based on where it's located on this chart, is present in all of these groups, but it wouldn't be present in anything ancestral to this phylogenetic tree. Yeah.
So is the first synapomorphy basically a plesiomorphy?
Well, so this synapomorphy here would be a plesiomorphy for these
That's what I
groups.
mean.
Yes.
Yeah, okay.
Yep, so synapomorphy 1 would be a plesiomorphy here.
And then 2.
Synapomorphy 2 would be a plesiomorphy here. Yep. Yep, so every synapomorphy can be a plesiomorphy, but not every plesiomorphy is a synapomorphy.
Gotcha.
Well, because if you get down to where you can't break this into any smaller branches, then, you know, those synapomorphies don't become plesiomorphies, right? Trinity.
So you put at each group you put a synapomorphy?
Yes. Yep, to support this branching. Yep, at each one of these, you put a synapomorphy to support this branching. If you can't come up with a synapomorphy, you have very little support for this branching. which means you have very little support for this phylogenetic tree. Okay? You should be able to come up with at least one synapomorphy to support your branches. Okay? Does this make sense? Okay, so synapomorphy 1 you expect to find in all of these groups here, but nothing ancestral to that group. And that's why synapomorphy 2 you expect to find in all of these groups here, but nothing ancestral to it. Okay? So synapomorphy 1 would be a plesiomorphy for these 3 groups. Synapomorphy 3 would be, or synapomorphy 2 would be a plesiomorphy for these 2 groups. Synapomorphy 3 is not a plesiomorphy for any group on our diagram. Unless, of course, this branched again. Alright? Is that cool?
Yeah.
Yes, sir.
Make sense?
Yes.
Cool. Any questions? Yeah, Michelle.
What do you mean by group in the definition?
What's that? I'm sorry?
What do you mean by group in the definition?
Oh, by group, it's this group that we provided here. So, like for birds, if these features are present in an ancestor that's not a bird, but something that you have to go further back to get to, then it would be a plesiomorphy.
Okay, and what is talents?
What is what?
Talent, the third word in the, what's called?
Talons.
Oh, talons are the claws, like the feet of birds.
Oh.
All right? No issues? Okay, so the remainder of chapter 22 talks about some additional evidences for biological evolution, and it references the fossil record and biogeography. Okay? The fossil record we'll talk more about in chapter 24, so we'll save that discussion until then. And then biogeography, we've already talked about, that's the distribution of animals through space. That's what Darwin noticed when he studied the finches on the Galapagos Islands, and how every island had a finch that was similar to a finch on another island, and they were all similar to finches on the mainland. That's the idea of biogeography, the distribution of animals through space. And so we've already talked about that as an evidence in favor of biological evolution, right? So I want you to know that you may be asked a question where you're held responsible for that. Where, for instance, you're asked a question about, the mammal assemblage in Australia. Okay? Somebody describe the mammal assemblage in Australia for us.
What is this?
Assemblage is just the collection of mammals in Australia. Yeah.
They're like extremely unique.
Yeah, and how are they unique?
Ow!
Oh my god.
Put another shrimp on the bobby. Yeah.
So like they just have all sorts of stuff that you don't see in most other animals.
Yeah, and so what do we call the mammals in Australia?
Dingoes.
I guess
Oh, I know.
like ancient animals.
Yes.
They already evolved.
Yeah, well, they are a that's an explanation. Yeah, marsupials, right? Marsupials.
Pouches, right?
They've got pouches. It is not the marsupials have pouches. It's not the only place on Earth where you find marsupials. You also find some marsupial species in South America, and then we have our own North American marsupial. Yeah.
Do wombats have pouches?
Yo, yeah, you bet they do. All right. So what's our North American marsupial?
Oh, what's it called? What's it called?
Ew.
The opossum.
Seahorse.
No, the opossum. Right? You know what I'm talking about? The opossum? Nasty rat-looking thing.
They have the tails. They hang upside down.
Yep. They do. Oh yeah. What's that? They play dead. Yeah, they play possum. Okay? And so, if you were to ask how the mammal assemblage or the mammal collection in Australia provides evidence of biological evolution, you can talk about that basically all of the mammals in Australia are marsupials, probably descending from an original marsupial species, okay, or maybe a couple of marsupial species that ended up there, although also ended up in South America, and that placental mammals never really got to Australia until we brought them there. Like dogs, rabbits, rats, cats, things that we introduced to Australia, and you can trace that historically. Yeah.
Okay, so this is kind of off topic, but it relates. Anyways, like, does Pangea have anything to do with that?
Oh, you bet it does. Yeah, you bet it does. And that was the one thing that we're actually going to talk about of biogeography in chapter 22 is Pangea, although there it'll come up again in a couple of chapters. The original supercontinent. Yeah. All right? Is that all right?
Yeah.
Okay. Can I erase this?
Yes.
That would be awesome. You could literally go through
Let's put it back together.
I want to go to Fiji.
Well,
Let's
see
recreate
that's
Pangea.
where the idea originally came from. Is after we had made really good maps and we were confident in the shape of continents, noticing that they fit together like a jigsaw puzzle, and then on top of that, they are very clearly moving. Some are moving more rapidly than others. We have two plates right underneath us that are moving in opposite directions. We've got one plate underneath us moving north. We have another plate underneath us moving south. The main North American plate is moving south. The plate that we're on, and I forget what it's called, with the San Andreas Fault. But then there's
Pacific
the...
plate?
It might be the Pacific plate. But anyways, it's moving north, and they move opposite of each other along that San Andreas fault line and some other fault lines. So, it's kind of fun. Yeah, Emma.
It's kind of stupid, but how do they move?
How do they move? Because they're floating on liquid magma. They're floating on the mantle.
How large? That's pretty.
I mean, the entire surface of the Earth is covered by plates. Even underneath the ocean, you've got massive oceanic plates. So some of them are really big, some of them are only sort of big, right? So that one of the plates that we're sitting on top of is one of the smaller plates along the Earth's surface. But it's still the size of like half of the state of California plus part of the Pacific Ocean. Yeah. Did I say specific? Oh.
Okay, so like in terms of like basically the idea of of it being one big supercontinent first came from this one guy who thought that like Africa and South America.
Yeah, also fit nicely together.
But then like I think it actually kind of finally came into a more defined idea when they started making the maps of the ocean of the bottoms of the ocean with that giant what is it called, like Atlantic Mid-Ocean Ridge or something like that. The one thing that like goes down the middle or something.
Yeah. So, all right. The idea is
Whoa, that looks
awesome.
It looks like an alpaca.
So the idea is that at the very beginning of our fossil record, the continents were separated, and then towards kind of the middle of our fossil record, they come together and form this supercontinent, Pangea, that then splits along the north-south boundary. Yeah.
So it came together.
Yes.
And then went apart?
Yes.
Oh.
Yeah.
There have been other supercontinents before Pangea.
Oh yeah. So it started separate. The continents started separate. They came together. Then they separated, and some of them have come back together. So like India was separated from the rest of Asia
Really?
until fairly recently, when India crashed back into the Asian plate and formed the Himalayan mountains,
And it's still growing.
which are still growing. Yeah, really, really quickly.
So it's like pressing together.
Oh yeah.
So Everest is growing.
Yeah, Everest
Yes.
is growing. I think isn't it like 1 inch of centimeter?
You know
per year?
what's cool is there's a lot of evidence that the Rocky Mountains, which have no peaks above 15,000 feet, that they used to be almost the entire range 30,000 feet tall,
So
and then have eroded away since they were formed.
because they're spreading apart.
No, they're all one plate now, but it's eroding away because of rainfall and other activity.
Rainfall.
All right, so the continents are all separate. They come together, form Pangea, and then they separate in north-south. Okay, and I'm just drawing blobs, but they separate into north-south. The north one is Laurasia, and the south one is Gondwana. And this is, yeah.
I think Pangea has an A between G and
It's alternative spelling, like archaic. You could do it with just the E or with the AE. Anyways, all right. Thank you, though. So Gondwana is South America, Antarctica, Australia, and Africa. Africa splits off first. And so then you have South America, Antarctica, and Australia. And where do you think you find the overwhelming majority of marsupial fossils? South America, Antarctica, Australia.
In the south.
Yeah. Oh yeah. And then think about this. Like you've got the ostrich, the emu, and the rhea. Like your massive, what we call ratites, flightless birds. And you find them in South America, Australia, and Africa. Yeah.
I know that like back in the prehistoric age,
You okay?
the time of dinosaurs, there was one dinosaur that I know lived in Antarctica during the time of like basically when it was a part of Pangea.
All right, I don't doubt that. We find whale fossils in Antarctica. We find a lot of marsupial fossils in Antarctica.
I believe that I think I did a paper on this all the way back in like 3rd grade when I was in the, I think it was called the Cryolophosaurus, I think.
I believe it. All right, yeah, Emma.
How many mammals live in Antarctica?
How many species of mammals live in Antarctica now? None. Sorry. I mean, we've got seals and we've got some seal species that live in Antarctica. You've got some whales that live around. So I don't know how many species, but it's basically just marine mammals.
Are there any plants there?
That's a good yes. But mostly in like the islands that are part of the continent. But yeah, I mean most of it is permanently frozen. But they're fish eaters. So
The plants?
no, the marine mammals that are there.
Well,
Yeah,
don't forget,
Tori.
So this is kind of a stupid question.
I love stupid questions.
But like, so you know how they were separated in like Africa and South America, and Antarctica, they were all separated into the south.
Yes.
How is it that even though they were separated together, how is their climate so different?
Now?
Well, no, like before, like, do you think that Antarctica before was like warmer?
Tropical, yes. And there's evidence of that with the mammals that are buried there. Yeah.
And so, but then it moved, so then they.
Yeah, and as it moved south and as the earth cooled, that it took on its current climate. Yeah.
How,
Go ahead, Tori.
oh well, no, never mind. Yeah, you can.
Why is the equator so hot?
Because it gets the most direct sunlight. So the sunlight that hits the earth at the equator is most direct. The rest of it, because the earth is tilted, so the rest of the globe gets indirect sunlight. Yeah. All right. Okay. What time is it? I have no idea.